This is John Buck. Welcome back to another discrete time linear systems video. And in this video, I'm going to talk about LTI systems, impulses, responses, and stability. We know if I have a linear time invariant system, the impulse response tells me everything I need to know about how that system is going to behave. It completely characterizes the behavior of the system for any input because I can take that input, convolve it with the impulse response, and find the output signal. If it completely characterizes the behavior of the system, it should also give me enough information to figure out if that LTI system is also stable once I know how to read it right. And in this video, I'm going to teach you how to do that. We're going to derive what the condition is for the stability in terms of the impulse response. And then once we have that, I'll show you a couple examples applying that test. Okay, so switching over to my whiteboard. Again, the topic for this, wrong color. For this example, I'm looking at LTI systems, impulse response, and stability. Basically, in a nutshell, how to look at an impulse response and decide if the system is stable or not. So again, we know if I already know the system's linear and time invariant, I need to prove that or I need to be told that. But if I already have that important piece of information, right, we know the output of the LTI system is based on the convolution sum. And maybe for this video, no, we'll leave it like this. We say, well, the condition for stability hasn't changed, right? We have bounded input, bounded output stability, which we sometimes abbreviate bounded input, bounded output stability. What that means is that that if we can put an upper bound on the amplitude, the magnitude of the amplitude of x of n, if we say the magnitude of x of n is less than or equal to b, then there exists, or we can find, a constant, say capital C, so that the output, the magnitude of the output is always less than or equal to that C. So if you tell me the input's always within plus or minus 3 volts, I can go off and use some formula based on my system and come back and say, oh, well then I can tell you the output's always plus or minus 9 volts or plus or minus 7 or whatever the formula is. Right? So to figure out if that's going to work, I need to say, well, let's assume, again, we assume, same basic thing we were doing for the proofs earlier with systems where we didn't assume they were LTI, but we're going to assume x of n is magnitude less than b. And now let's go ahead and we say, well, the magnitude of y of n, I can just take the magnitude of each side. On the left-hand side, I have y of n. On the right, I have the convolution sum. Right, so I write out the convolution sum and take the magnitude. And now I just start to get good use out of all the properties and inequalities about magnitudes I know. For example, I know the sum of a magnitude of a sum is always less than or equal to the sum of the magnitudes, right? So this has to be less than or equal to the sum as k goes from minus infinity to plus infinity of the magnitude of the argument. So I've got h of k, x of n minus k inside the magnitude. And this is heading in the right direction, right? Because I'm trying to find an upper bound on y of n. And so I'm saying, well, right now y of n is less than this. Let's see if I can keep working it. We say, well, the magnitude of a product is equal to the product of the magnitude. So now I can say that I've got the magnitude of h of k times the magnitude of x of n minus k. Well, if x of n is bounded by b for all times everywhere, then it means all these shifts and flips of x of n would still have the same upper bound on the amplitude, right? So I can still look at this term here and say, well, this term is always less than or equal to b. So if I put that into the sum, I say, well, so this sum here, the sum of the magnitude of h times the magnitude of x, is always less than or equal to the sum k goes from minus infinity to plus infinity of h of k times b. And I can factor that b out front now, right? I don't need that b inside the sum because it doesn't depend on k anymore. So I can say this is now equal to b times the sum as k goes from minus infinity to plus infinity of h of k magnitude. Right? So we say, well, if I trace this back, I've got a chain of inequalities all going in the right direction. So I'm saying the magnitude of y of n is always going to be less than b, which is the upper bound on the magnitude of the input, times the sum of the magnitudes of h of k. So we say, well, this when is this finite? That's what I need to know. We say, well, as long as that sum of h of k's is finite, as it works out to some finite number, that means I now have my upper bound on the output, right? So if the sum of the magnitudes as k goes from minus infinity to plus infinity, so the magnitude of the impulse response x of k is less than infinity, that is, that sum converges to something finite, then the system is stable. Right? Because I'm getting ahead of myself. I jumped a step there, so let me break this down carefully. Right? If h of k is less than or equal to infinity, then what we've shown is that the magnitude of y of n, the output magnitude, is bounded. And a bounded output means that I've got a stable system. Right, so if I fill in the dots there, or connect every system is stable. Okay, so let's see a couple examples. Again, the same one I did on the causality video. And so if I guess if I was smart, I would have copied the picture over already, but I didn't. Not planning that far ahead tonight. But right, we saw last time, this is this decaying exponential that turns on at time 0 and then goes 1, a half, a quarter, an eighth, and so on. And so the question is what we need to figure out is the sum. We can do the sum over any variable, it can be over n or k. It's just a dummy variable within the variable of a sum is just like the loop variable of a for loop. So is the sum of the magnitude of the impulse response less than or equal to infinity? I guess a vocab word we should mention here. People sometimes call this absolutely convergent. So absolutely convergent. Right, so if I plug in for the magnitude of h of n, well, these are all positive, so I don't even really need to worry about the magnitude. And then I can say, well, this term here, the u of n, this equals 0, right, when n is less than 0. I've got no values in the negative time here. So I could simplify my sum to be the sum as n goes from 0 to infinity of 1/2 to the n. I look at that and I say, ooh, I know that one. That's a geometric series. In fact, it's an infinite geometric series. And so this is equal to 1 over 1 minus 1/2, which is 1 minus 1/2, which is 2. Right? And 2 is definitely less than infinity. Right? So this is enough to say, so based on this, since the sum converges, based on this I can say the system, since h of n or since the sum of h of n converges, the system is stable. Okay, so that's our first example. Let's look at one more. H2 of n is equal to u of n plus 3. And we already saw on the causality video that this unit step has been shifted left by three samples, right? So this is, instead of starting at 0, this unit step turns on at -3, and then goes forever after that. Right, so this is just equal to 1 from everything from -3 onwards to the right. Right, this is my h2 of n. So that says if I was going to check the stability, I need to ask, I say, well, is the sum as n goes from -infinity to +infinity of the magnitude of h of 2n less than infinity? Well, let's plug in and see. From -infinity to +infinity, the sum of magnitude of h2 of n is u of n plus 3. But we've seen up here already, right, this unit step is either equal to 0 before -3, or it's equal to 1 everywhere above it. Well, if I take the sum from -3 to infinity of 1, that goes to infinity. So it's not bounded. So the sum of the impulse response here is not bounded. So we can say since the sum over all n of the magnitude h2 of n goes to infinity, the system is not stable. So bounded inputs could give me unbounded outputs. Okay, again, so that's the main points for the video today. If I have an LTI system, I can look at the impulse response and using the convolution sum, figure out what the rule is for when the system will be stable. And that is, the system will be stable as long as the magnitude of the impulse response sums to a finite number. Okay, so that's all for this video. I'll see you next time.